Dr. Tripathi, can we start?
Good morning, ma'am. Yes, we can start.
Okay. A very good morning to one and all. I'm Bhargavi, convener of this 6 days virtual workshop on characterization, advanced characterization tools, fundamentals and applications. This is the third day, and on behalf of organizing committee, our principal, staff and students, welcome. Today's our eminent speaker, the resource person Narayan Tripathi. I welcome you, sir.
Thank you, ma'am.
I also welcome all the participants, academicians, university and college teachers, research scholars joined here for this event from different universities and colleges and research institutes. I welcome you all to the third section of this virtual workshop. As you all know, this workshop is jointly organizing by Pandit Shyamacharan Shukla College, Dharsiva, Raipur, and C.V. Raman Global University, Bhubaneswar. And today we have a very interesting talk on X-ray diffraction, and our eminent speaker is Dr. Satyanarayan Tripathi. He will be delivering on X-ray diffraction and its applications. And before asking sir to present his talk, let me introduce you with a brief introduction of sir. Dr. Tripathi has done graduation in science from BJB Autonomous College, Bhubaneswar, Utkal University, Odisha. He has done Master of Science in Physics from National Institute of Technology, Rourkela, and awarded with doctoral degree in 2015 from IIT Rourkela. Then after, from 2014 to 16, he was with postdoctoral fellowship from Institute of Physics and Center of Education and Disciplinary Research, University of Silesia, Benkowa, Poland. He has more than 20 publications in international science citation in journals of high repute. He has qualified aptitude test in gene physics in 2000. He is also a national topper in exam conducted by Indian Association of Physics Teachers in 2006-7. Dr. Tripathi, the topper in BSc Honors, he has completed 22 courses on material science. Presently, he is work assistant professor in Department of Physics, Sri Sri University, Cuttack. With this introduction, may I now request our speaker, Dr. Tripathi, to present his talk. Sir, please.
Yes, ma'am. Thank you. My voice is audible clearly?
Yes, sir.
Okay. Okay. First of all, I'd like to thank you to the organizing committee, principal sir, Dr. Bhargavi ma'am, Dr. Tanmay Badapanda, and all the members, faculty members at the Department of Physics, Shyamacharan Shukla College, Raipur, and for the invitation to present a seminar on diffraction techniques, and we will do a virtual workshop on advanced characterization, fundamentals and application. I hope everybody is aware of diffraction method, its technique. Today I am not going to describe about this basic literature. Rather, I am going to discuss on practical application, how you basically enter data, how you basically understand what are the information extract from this XRD data. So this main focus of the talk is the crystal structure determination from the samples and the microstructural. These are the main focus of this presentation. So today we'll see different types of samples we present the analysis. So next slide will basically tell what are the things that the parameter what from the XRD data. First of all, the phase composition of sample. Suppose you have peroxide structure, you can determine basically the FbO3 type structure can determine the chemical formula and you can determine. Next, you can determine the unit that is basically this is called the indexing. This can be by calculating positions of XRD. Suppose you have 6 sample and you want to know the so because there is reference patterns, I talk about the sample variant pattern. So you have synthesized variant pattern and the exact pattern you obtain the critical variant crystal structure information file. So you basically find that the crystal structure of your own site. Next is some structure analysis like axis mixture orientation of the lens. The thing is crystallized and microstring. So there is first determine the crystal size. One of the methods is here. No. And next is some hollow then four method. Okay. So you all these things information we basically require. So now I'm going to show you one single X-ray diffraction pattern here. As you can see here, there is X-ray diffraction pattern. So X-ray diffraction pattern basically there are so many peaks. Okay, so all the peaks are basically varying from 10 degree to 40 degree here. So there is a background, there are peak positions, there are peak shapes, and there are peak intensities. So the peak position we can calculate the unit cell or unit size. From the intensity we can calculate the attribution of the unit cell, basically the structure factor point of view. And the next is peak, we can calculate the particle size and effects. Okay, so these are the basic information we can calculate. And important thing is that different types of data we take, we basically take the data for a crystal or we take data for amorphous or a gas. So based on that we will have different types of background. So today we are going to see how we are going to model all this kind of parameters. So that is the major basic theme of the seminar. So as you said, so there are different varieties of materials are there. So for a crystal, there will be sharp peaks, the intensity will be really high, there will be different peaks from 20 degree to 80 degree you take for example, and intensity for a amorphous sample or liquid sample, because there is no long range, there will be hump. And for the gases, there will be a simple a decreasing function is like exponential decreasing function. So it will be like monatomic gas because they basically scatter at low angles rather than high angles. So these are the basics we have from the our studies from the textbooks. Okay, so I would like to tell that here, so the intensity of a pattern basically depends on the following factors. That one is their multiplicity factor, polarization factor, Lorentz factor, absorption, and the temperature factor. All these factors basically influence intensity of the powder different pattern. Okay, so I'm not going to tell you about this details about this Bragg law. I hope you all studied the 2D sin theta n lambda. So these are the basic things you require to understand and interpret the data. My main focus is how you interpret the data. So one of the techniques what we follow is basically the Rietveld method. What actually Rietveld method does to us? Okay, so basically it calculates. Suppose we have a X-ray diffraction pattern, right? So you have a experimental data. How you collected data? You collect for a polycrystalline sample. You collect the data from 10 degree to 90 degree with a very slow scan rate, and the sample background has to be very good, and the distance between the two data points has to be very close. So what actually Rietveld method does is that it calculates the intensity based on different parameters. So the first parameter you can see, this is the background parameter. Second parameter is S, is the scale factor. H, you can see H scale, these are the symmetry, this Miller indices factor. Then theta is the correction factor, experimental geometry factor. Then this is the structure factor F, and P is the profile function. Okay, so in structure factor it will include atomic position, site occupancy, thermal factors, and in profile function you have particle size, strain, all the instrumental resolution. So whenever I talk about instrumental resolution, I'll basically discuss about each and every parameter. I'll also discuss how to do this kind of refinement by your own. Okay, so when we take some XRD data, we always know that the instrument is also going to affect us. Means the thing which we are measuring, means with the, like suppose you are having Chicago or you are having Pananalytical, this instruments, these instruments are also going to give us some effect on our pattern. So we have to also remove that effect. So how we are going to do that, we are also going to see. So next is in Rietveld method. So there are different parameters which we basically require to understand how the good fitting is good. Okay, so how our experimental data is basically close to the theoretical data. So these are the various factors are there, that is RP, RWP. These are basically the ratios of intensities, and this goodness of it ties is also the ratios of intensity. So here n is the number of pre-parameters, P is the parameter. There are some involved are there. So these parameters will basically tell you that how this fit means we have XRD data. So how by employing how we are going to match our intensity to the experimental data. So this is our main task in. So details of the theory you can find in Young book, Rietveld book. So you can go there and see that, but I will show you how to do this method. So to do the Rietveld refinement, what are the first is a high quality experimental diffraction pattern. So for this purpose, this is the most important part. So for this purpose, what you need, that you should take the data in a very small, means time has to be very large during taking a small reading, 3 degree per minute, 4 degree per minute. The distance between two data points is like 0.01 or 0.005. It's up to your choice. So next what you must have, I would like to remind him that the sample quality, the data quality has to be good, and this makes a really, if this is good, your refinement will be good. This is a major thing. So the next thing is the structural model. Suppose you synthesize bismuth, ferrite, lead, iron niobate, or sodium bismuth titanate. So all the samples they have synthesized by different researchers. So what you have in literature, you can find a prior model, like suppose I say bismuth ferrite or barium titanate. Barium titanate structure is tetragonal structure. It has P4 mm. P means primitive, 4 means this is a symmetry, mm means mirror reflections. So there are symmetry in different directions. So these are both that I mean. I'll show you how to read a CIF file. So what you need for refinement? First, you need a high quality data. Second is you need a structural model. Okay. Next is a good background function. So these are the three things you basically require before starting a red belt refinement your sample. So many of you have research, so you must have collected some XRD. So these are the first three things you must know. So your sample has to be very high quality data. Good, then everything will go smooth. Okay, because rest second part, third part is just a software related thing. So tell you about how to do this red belt refinement using package. Okay, so basically you are going to basically need three things. Okay, first is crystallographic information file. So what is a crystallographic file? In a crystallographic information, let me show you. I think I have opened so many crystallographic information file. I think I'll show you this one. So I hope this is visible to all of you. So this is a crystallographic information file. So here I have actually I have downloaded this one in one database, that is where I have downloaded. This is AMCSD database. I'll tell you where to download after this. But now I'll show you to understand this CI files. So this sample is called bismuth ferrite. So author name is there who has discovered this. So this is a long back. This discovered 1971 fraction, and it says that here A, B, C are this values, and your alpha, beta, gamma are 1991. Your experimental, sorry, this is theoretical density. This place group is R3C. R3 means rhombohedral, and 3 means this is a symmetry, and C is a glide. Okay, and these are the symmetry available, and here that bismuth is staying at the center. Oxygen. Okay, so this is the way suppose I need bismuth ferrite, Bi I type, then iron is there, then oxygen is there. If you want to put any other restriction, you can also do that. Then you the send button. Okay, so after this, it is going to give me so many results. I hope this is visible to all of you. This CIF files which I have made a query in the crystallographic open database. Is it clear to all of you? Can anyone say yes, so that
Yes, sir.
okay, very good. Yeah, so these are the crystallographic information file you can access from COD database. Okay, so this thing you require, you can download it here from directly clicking the CIF file. So if you click here, you can see that yes, these are available which I was talking about, and this is the crystal structure. So this is the model you have before you synthesize your sample. Means you have your data. Now this is the model you are going to overlap your XRD data, and you refine it, and you collect your own data. Okay, so I'll go back to my slide. So there are different databases. I hope you remember this. These are very, very important. Sorry. So one is crystallographic open database, then is American Mineral, then is Material Project. These are extremely important databases databases, where in materials project you can also access various type of theoretical like quantum espresso information you can also access. That's out of this syllabus. Okay, so this is one. Next, so for Rietveld refinement, first we require a model CIFI. Just I showed you. Okay, so if you want to see the model, you can see I have imported this bismuth ferrite database. So this is the structure. It is the way it looks, and this is the bismuth ferrite BiFeO3. This is a sample. So this is my sample. So these are the atomic position. These are the occupancies. These are 6A means Wyckoff sites. 6A, 6A, 80B. As we go on, I'll tell you how we basically understand this Wyckoffs. Okay. So yeah. So first of all, you need a CIF file. Then is you need to convert the file to a PCR file, because the foolproof practically runs the PCR file. Okay, and there are different refinement steps. I'm going to discuss with you one by one. So this is very important. Okay, this is the how to download the crystallic information file. If anybody requires this link, I'll also put an email to me. I'll send this. Next is how you describe the crystal structure. By describing the crystal structure, I mean that I need a space group of the sample, I need the lattice parameters, I need the atomic position, I need atomic occupancies, and I need the thermal parameters. So these are the parameters I require for the refinement or the determination of crystal structure. So these are available in the crystallographic information file. Suppose some people they synthesize their own sample, like new sample. So in that case, crystal structure determination method is different. Okay, we have to charge density plots, then we will understand. Yeah. Next is there are various refinement steps which we are going to follow. So first thing is scale factor. Suppose I will tell you that you have synthesized a sample, the maximum peak you obtain like 100 or 200 counts, right? Density is arbitrary units, so you may get 100, but the theoretical pattern which will refine it may have 1000. So you have to scale down the theory pattern to the experimental data. So that is called scale factor. So the second thing is 0-point detector, then background parameter, lattice constant. These are the things you are going to refine. Then the next step. Next is atom position, overall D/Wall factor, then peak shape, peak asymmetry, atom occupancies, then isotropic thermal parameters, background parameters, microstructural parameters. You basically refine these things step by step. So these are the way we are going to for the Rietveld refinement. I am also going to give you a demo how to do that. So what we, in conclusion, I like to tell, need a sample file, we need a high quality data. I would suggest all, because that collection of data is very, very important. All the XRD data, they are not fit for Rietveld refinement. Just if you want to do Rietveld refinement, or collect data which has very high quality, step size is very low, data collected in very small scan range. That is important. Okay. So now I'm going to show you how to do a Rietveld refinement. I'm not going to go in more deeper, but I'll tell you how to start it. Okay. I hope all of you are watching this. So this is very important. So I'll show you. So this is my foolproof bar suite. Okay. So what we do, first we check our data is correct or not. So here I have a sample of bismuth ferrite, which is a peroxide structure with a rhombohedral crystal system, and many extensive studies have been done. So here I have open WinPlotter. I just like to see how the data looks like. So to see a data, you go to open pattern file, then Instrom, then go OK, and then I go to the desktop. One sample is there, data is there. I click the data. So this is the way the data looks in WinPlotter. Okay, and I am going to analyze this data using a model of CIF. Okay, so what I do, so EIF, in basically doing the Rietveld refinement, what we basically do, so we open, so let me minimize this. So there is a EDPCR file, so I'll click that EDPCR file. I hope it is correct. Yeah, I hope you see this. Then there is a converter from CIF file to PCI. So readbuild basically allows us to convert the CIF file to the PCR file. So very important step. Don't create your own PCR file by modifying others file. You go for a transformation from CIF to PCI. So you go to the desktop here, and here I have a CIF file. I double click that. So here you can see the system is automatically taking the instance my lattice parameters. It has imported to the system, and this is the atom parameter it has already imported. This is clear, right? So next is you click it OK, right? Then you go to the general. You can change this name. There is no problem. You just make it OK. Then go to the pattern. Here you go to this data file. Okay, so here you have to show the path of the data file, and you can say this create yes, and this is your data file. Next is in refinement solution. This refinement, you click on here XRD, and because we are having copper, so these are the two wavelengths, copper alpha 1, okay, alpha 1, K alpha 2, and here in pattern you just select any of the peak function. Most of the vector peak function basically a pseudo, or you can go for this TCS function. This is fine. Okay, so you can click then, and background type here 6 coefficient polynomial is a good one. You can go for, if you have more data on the background, you can go for a 12 coefficient. So first of all, to tell that if you change the first parameter of the polynomial function, basically it will feed the data. You don't have to feed all the parameters like the 6 coefficients here. First parameter is enough. Okay, so there are different methods available where you can create that. So you plus OK. Next is geometry. You can see here if you want to put a incremental resolution file, you can put the browse here. You can do that. Okay. So next is you put OK here, and to see the page, because I have a Bismuth ferrite, right? So you have to put here provided by the user and contribution pattern. You select it here X-ray, and you go down to the same function which you selected, this TCS function. Okay, and this is OK, and you just check the sim here. This is my Bismuth ferrite structure, so make sure that you have a R3 structure. Okay, you just double click here, so all the symmetry positions will come up. Just make it OK. Okay, so this is single phase. Tell about how to do a dual phase refinement. I'll show you some of the data. Okay, so this is I'm going to do OK, and next is refinement. So in refinement, what you basically going to select number of cycle. You can start from 6, 10 based on the it will refinement cycle. People often ask me what is the number of cycle you basically choose. I suggest that you start with 10, because by your own experience you will decide how much run is required to fit your data. You will understand while I run. So this force termination you can go to 0.3, and the others you can go for criteria not matching. Then you have a background function. You can see that this is background. Then is instrumental parameter, which I was talking 0 parameters, scale parameters. Then you go to the atoms. You can see all these atoms are present. Then you click. Then next is the profile. Profile, there is a scale factor. Then ABC parameters, asymmetry parameters. Then preferred orientation parameters. All are available. And you click OK. Then it's OK. And save it. If you save it, then it will create one PCR file. You can see PCR file is created, right? So what you can do, you can go for a refinement. So what I do, I just click the data. Okay, so it will automatically, it may take some, yeah. So the data started to run. So what my next suggestion is, you just check all these peak positions are coming at the right location of the peak below or not. What I wanted to see here, you can see that here data, this is black line is my theoretical line, this red line is my experimental line, and this is my brag position. So you just make sure the peak is coming at the same position experimental peak or not. That is very important. Okay, So this is the thing. Here you can see R3C, there is a characteristic peak, this one at 39 degree. So you make sure that you have the right peak or not. So first thing you must do that. And beginning of run, you will find a very high R factors. So don't worry, this is the first run we have. I'll tell you in 110 systematic process how to achieve the lowest R values and what are the R values are reportable for the for the paper. So this is okay. So the first thing you should refine is the profile parameter. If I refine the scale factor here, you can see automatically the theoretical XRD pattern and the experimental XRD pattern, they will converge on each other. You can see that this theoretical XRD pattern is now converging on the experimental. Okay. So you can see, yes, in the normal ending. So it is now saved. So I'll save it again. So I run it again. I hope you can see the peak is coming at the right position. I hope this is clear, right? So peak are coming at the right position. So you can see this peak is coming at the right position. So everything is fine. The scale is now adjusted. Okay, that is very important parameter. Okay, and now we have chi-square is this much, RPRW this much. We'll see how to go for more. Okay, so you reload. Next is you go for background. You just try to feed the fast parameter. That's enough. Okay, fast parameter, and in instrumental you select 0. So if you do that, so you save it. Let's see what will happen. This is very important. You can see now what are the instrumental corrections that it is adjusting. Okay, so my background is actually fitted correctly because I refined the fast parameter, so my background is getting fitted. So until it converges, I'll basically run the data. Okay, so you can see my chi-square is 12 now, my RPRW this much. So I can see that the peak is coming at the right place, and there is a problem at the peak broadening because this is a shape parameter. What we call the shape parameter will come into the picture. We have the peak positions. Now we will play with the peak shape. So if let's go to the peak shape. Where the peak shape is present, it is present at the profile. So what you need to do, you can, for better peak position, you can refine the lattice parameter. So let me first define the lattice parameter. So there will be a little bit of change if we do that, because it will adjust your experimental value to the theoretical value. I have another one. It is fine, no problem. Yeah, so you can see that lattice parameter is now refined, right? So I close it. So yes, then I go to the peak shape. So peak shape is X and Y. So if you do that, you can see that the lower end of the peak will be fitted. So this is okay. So next, if you see that, so next you see that my data is almost finished. I hope all of you have seen what is the procedure I have carried out to feed the rebuild data. Is it clear, all of you?
Yes, sir.
So this is, yes. So this is the basic requirement. You can go for the norm because it is not saved. So you can go and you can save it and you can do it again. So see, there are so many parameters available. So major basic parameters, why you refine it, that is important. So after this, you can see the RPRW are coming 2027 and chi-square is 1.83. You can define more, but I'll not go more. I'll show you how you basically collect the information. Okay, so you close this and go to the output, and here one important file is summary file parameter. So here you click this one, and then I think another thing I basically require HKL. So here you click this. So okay. So save it and you run it again. I think, yeah. So after you do this, what will happen? Let me do my own sample folder, right? So there are so many files created here. So require basically the sum file. That is the most important file. Okay. So if you see the file, it will collect all the summary of the information. So you can calculate the lattice parameter here. So lattice parameter is 5.57572. So here this is the error part. So A, B, C are available. Positions are available. You can refine the positions if you like. Okay. Next is occupancies. I forgot to take occupancies means suppose bismuth ferrite BiFeO3 Bi1 Fe1O3. Okay, so they are located at 6A 6A 18B. So the occupancies will be 6 6 18, or you can take 113, or you can take 0.31. It is up to your choice. Okay, so here at the end you will see one analysis statement. You will see that your refinement could still be improved. Here it will also say that you can have a better refinement. Okay, it will say that refinement is good. All the statements will come up here. So from this you can basically calculate all this. Yes, from all this you can calculate your RP RWP. You can see RP RWP is 13.6 and this is 19. Your chi square is 1.69. You can refine more to have better value. Okay, so what? Yes, anybody would like to ask something?
No, sir, please.
Okay, so let me close this one. So one other file is PRF file. You can check it here. So this is the data you will get, and here if I click it here, if you refine the asymmetry parameter, you can go for a better fit. You click it here, you will get the lattice plane and the positions, all the things information you can get, and here these fittings are available. Okay, all these informations will be available, and you can still report this data, and better you go for higher refinement. So now what I am going to do, I am going to show you the Rietveld refinement results of different kinds of sample. So starting from ferroelectric to magnetoelectric, all different kind of data, and how you basically analyze the data. Okay, so this is the refinement part, how we basically use the data. You can also plot this data, like you can using a Vesta software is available. You can import your CIF file, and you can get the structure as you like. It's very easy there. Okay, so what we discussed up to now is that how to refine, how to collect the data, how to refine a data, where to get the model, the CIF file, and what are the steps that are needed to be followed. Okay, so now I am going to show you some of the data. I think this is a very old data I had. So this is about the structural properties of single phase bismuth ferrite. This is an old paper I published in Material Chemistry and Physics Elsevier in 2013, as well as it is published in JAP 2013 also. So what I took here, so I had collected my XRD data. This data has been collected in Pan Analytic, and the sample step size was 0.02, and this data collected from 20 to 80. So in bismuth ferrite, we have basically 3 ions. Okay, 2 cation, 1 anion. So bismuth, this iron is there. Bismuth is located at the z-axis, iron is Z, and this is the atomic position. As per the Mega-Darlington formalism, this is a very new way to refine the crystal structure of bismuth ferrite. It has an R3C structure. It is a perovskite material. It is a rhombohedral distorted structure. Okay, so literature basically tells about this thing, and this is the crystal structure available in the literature. So I have collected my data. So my Rietveld refinement, what I have done, you can see this is the Rietveld refinement of the bismuth ferrite sample, and here y-axis intensity, x-axis 2 theta. So here dots are observed, black is calculated, and the gray line below is the difference and the Bragg positions are here presented. And one of the characteristic reflection 113, which is arises due to the, because bismuth ferrite is AbO3, so it has BO6 octahedra. Okay, so due to that rotation, this plane coming, so because these are oxygen planes, so this is a less intensity. So this is our this is our FESM figure. This is the way sample has been carried out, and this data has been reported in material chemistry and physics. With this data basically matches to the previous reports. So we basically confirm that if the matching, if the experimental data is fitting to the theoretical data, then we know that yes, this data is fitting, and this is the crystal structure. These are the lattice parameters. So this is the crystal structure sample. You are going to basically get it. So this is, these are basically, if you want to show this in paper, it is fine, but you can do easily with this software available. This is called Vesta software. You can easily change the box size and you can present it. So this is not that much matter to me. So next is this thing. So what I have shown you right now is that the single phase bismuth ferrite is a peroxide structure. So single phase things are not that much a problem. Okay, but when we talk about solid solutions, so this is a sample about structure and about bismuth ferrite and gadolinium manganite. So here we basically synthesized our sample from 0.0 to 0.02, and the step size was very slow. And this is published in 2020-21, I think, Material Research Express, IOP. So here I'll tell you, there are different techniques. It is easier to do single phase refinement. If you have a standard CIF file, you can easily do that. But if you have a different kind of solid solution, means suppose you have a bismuth ferrite, what we are doing, we are doping bismuth ferrite at a site of the peroxide structure with gadolinium, and in iron we are doping manganese. Okay, because of the ionic size contributions. Okay, so we know that gadolinium will go to the B site and manganese go to iron site. Next is what this gadolinium will do. Gadolinium is basically a rare earth element and bismuth is basically non-rare earth. It has a 6s2 lone pair. So whenever gadolinium will go to the bismuth site, it will create a chemical pressure. It will make inactive the 6s2 lone pair of bismuth. So what will happen? There are so many changes, crystallite changes we are going to see. So for single phase refinement, I'll tell you, I'll show you the data. For single phase refinement, what we do, for less composition, I'll show you how I decided this kind of compositions also. So up to 0.075, the structure is R3C. How you will know that? You will know that, let me show you the XRD figure. So I hope this XRD figure is visible to all of you. So this XRD figure tells that all the XRD pattern up to 0.075, they are similar. There are no splitting of the peak. There are no shoulder of the peak. There is not much peak shifting. All these things are not happening. Only the peak broadening will be there because of some chemical pressure or the strain effect, because you are introducing some substitutes. So it is going to introduce some strain. So some broadening will be there. Double peak will come to single peak. So these are the effects of strain. Okay. So what is happening? You can see that I have given a this right hand side one picture 36 to 42 degree. You can see that one characteristics reflection of R3C phase is there up to 0.075. So we confirm that up to that point, since the XRD pattern is not changing more with gadolinium manganite, so we are actually doing this structure R3C. We are keeping R3C structure for refinement. And when you to do that, you place bismuth, this bismuth side gadolinium, you use the same atomic position, and in case of iron, you use the same atomic position as manganese. There will be 5 elements. Okay, so what we are doing, we are actually seeing a BO3 type structure that may be bismuth ferrite, that may be gadolinium manganite, that may be bismuth manganite, or that may be gadolinium ferrite. So all this kind of structures are possible. So we are going to give out this kind of atomic positions. Okay, so here the structure doesn't change because XRD patterns are similar for X. Okay, so this atomic positions have been collected from ICCD database, so you can take if you are doing work with bismuth ferrite. So next is after X is equal to 0.075, we can see that here in XRD data there are splitting of the peaks, there are new peaks, and there are serious broadening in the peaks, right? So these are actually indicating us that new crystal structure has arrived to our parent system. So what is that possible structure? So the most convenient way is that whatever the dopant you have used, suppose I have used gadolinium manganate, you see the immediate structure of gadolinium manganate, or any high temperature phase of bismuth ferrite. So here you see that in dual phase, what will happen from 0.021 to 0.02, I have used R3C phase. In place of gadolinium, I have put bismuth. In place of I have put manganese. So these are the atomic positions, right? Now, when you change or dope something, and that is evident from the new reflections, you basically use this one. This is basically gadolinium manganite atomic positions. Okay, so you basically A side, because you don't know where the gadolinium will go, it will go to the A side. It may be bismuth, it may be gadolinium. So you have to give the both the probabilities. Okay, so this is basically this structure is a very this structure is available basically for the rare earth manganites and yttrium manganite, gallium manganite, dysprosium manganite. All the structures they have PNMA kind of structure. Okay, so we basically, this is the XRD data. So based on that, we have done the Rietveld refinement. And next, what we have done, we have calculated the lattice parameters as the way I have showed you in the refinement process. And next is how to analyze the data. So what I have done here in x-axis, I have plotted a pseudo cubic lattice parameter versus composition. Pseudo cubic lattice parameter is basically, suppose you have a R3C, you basically go for the volume. Volume will be 374 angstrom cube, and there are 6 unit cells. So if you go for the primitive one, you have to divide that volume. Okay, so that is a primitive volume, and you have to take root cube, so that will be a primitive lattice parameter or pseudo cubic lattice parameter. The major thing of using pseudo cubic lattice parameter is that it will reduce down to your cubic size, like use cubic size. Okay, so that will help us in analysis. So you can see that with increasing composition, okay, the lattice parameter decreases. Okay, and at x is equal to 0.1, both the phase exist, and both the phases have maximum value at x is 0.5, and that is called the morphotopic phase boundary. So I would like to tell that a morphotopic phase boundary is something both the phase coexist and they have different maximum properties. Here I can this actually I remember bismuth ferrite is around 70% and gadolinium manganate is around 30%. You can also calculate that from the Rietveld refinement, and this S and T are the displacement of bismuth and this iron, so they are coming minimum at 0.15, and this is like S minus T is related to the order parameter polarization, so that is coming to 0 because this polarization of the system will, because it's a centrosymmetric structure, so polarization will come down 0, so that's why we are having a decreasing part. Okay. So this is a doping structure, like this is called a solute solution of bismuth ferrite with gadolinium manganate. So this we have done this dual phase refinement, we have analyzed the data. Okay, so the next data I am going to show you is basically the same system bismuth ferrite but with dysprosium manganite. This paper I think we have published in JAP 2013, 2015, again also 2017. So this is a very good paper, and here also what we have done, we have same XRD pattern here. We have refined the crystal structure of this system up to R3C up to 0.075. After that, we have used PN21 phase group. So we have done the dual phase refinement. And as per the similar explanation I give you, because with dispersion will go to the bismuth site, we will create a chemical pressure, and the XRD patterns are similar to the parent structure. So we take R3C space group. After that, new reflections are coming. So that is a part of DYMNO3. So we use PN21 space group. We could have used PNMA, but this structure is non-centrosymmetric. We obtained a ferrolytic hysteresis loop, so we did not use PNMA because of the non-centrosymmetric nature. So this is the dual phase refinement of the sample, and this is a paper published in Journal of Applied Physics. You can see that, and these are the lattice parameters we obtained. All this RPRWP. I would like to tell you regarding RPRWP. You can report RPRWP below 10 or below 15. Your chi-square may be 1 or 2. Okay. Suppose your data has very high quality, you will get chi-square even 5, 6. Make sure that your RPRWP is below 10. They are the Bragg factors, so they will come 10. Okay. So this is the lattice parameter versus composition. So you can see that both the lattice parameter decreases, C and A. So this is normalized lattice parameter A, B, C. So I have normalized them. Okay. So to give them to an equal magnitude. So both the lattice parameter decreases, and at x equals 0.05, 0.15, sorry, 0.1, we have basically the morphotopic phase boundary. Okay, so these are very important explanations. They are very important plots where you can understand how the compositional structural phase transitions are happening. These are all compositional driven structural phase transitions. So make sure that you do the right radial refinement and you choose the right space group to come up to this explanation. Okay. Next is another very interesting space group is called this NBT structure. Okay, so NBT is a very peroxide structure. Barium titanate is a peroxide structure. Basically, people nowadays they do this kind of structure for the relaxer studies or this morphotopic phase boundary to have better piezoelectric all these properties. Okay, so what basically does sodium bismuth titanate is a R3C structure. If you do the polling, it will have CC structure, means monoclinic structure. So sodium bismuth titanate, we are using barium titanate. If you do that, their structures, different structures will coexist. So the sodium bismuth titanate is having R3C, barium titanate is tetragonal. So we can see a tetragonal and rhombohedral coexistence. Okay. So here I have shown one of the atomic positions for the refinement. So this is for A site AbO3 barium sodium bismuth titanate, and this is for P4MM tetragonal phase. These are the atomic positions we have used. These things you can obtain from the crystallographic information file or COD database. Okay. So what we have done here, you can see the data up to 0.05. The peaks are actually equivalent to sodium bismuth. Here we have doped sodium bismuth titanate with barium titanate. So barium will go to A site. It may go to bismuth site. It may go to sodium. Titanium will go to as usual B site. So up to 0.05 there is no structural change. But after, I go to the next slide. After 0.06 we obtain new peaks are appearing, new solidus are appearing. So this is the page of barium titanate. So we fitted with R3C rhombohedral plus P4MM tetragonal space group. Okay. So these are the refinements we have carried out, and what we obtained this graph. So this graph is basically pseudo-cubic lattice parameter. As I have told you, this lattice parameter is basically the primitive cell volume, and you make a cube root of it. And this is the composition, and you can see up to 0.06 below we have R3C phase, and after that we are having dual phase, and most of the phase is appearing at 0.08 or 0.07. This is actually critical stage. So most of the people they report 6%, 7%, 8%. Whatever the results we obtain, it is the 7%. Okay, you have the morphotopic phase boundary, the crystal symmetry of the sodium bismuth titanate is driven by barium titanate to a morphotopic phase boundary to give better ferroelectric, dielectric, piezoelectric properties. So if you have this kind of data, it will easily support your electrical measurements. So that is very important. So next is another type of sample is DY doped NBT-BT sample. So here we had what is their sample? Actually 6% barium titanate and 2% of sodium bismuth titanate. In that, this is basically, I'll write it. So this is 0.92 and this is 0.8. So this is the sample we are dealing with. So here we have doped the dysprosium. So you see, dysprosium, it can go to the sodium side, bismuth side, or barium titanate side. We don't know, but we are going to show you how this is going to come. Okay. So if we dope that, here we observe that dy enters into the A site of peroxide structure. How we understood that? We can see that from lattice calculation, the lattice parameters in P4MM phase remain constant, whereas R3 phase decreases. Okay. So this basically allows us to say that dysprosium is not going to the BS side, that it is going to sodium or this bismuth side, and because R3 phase is decreasing, so it is actually going to that. So this kind of information we got from this where the atomically stays. Next is another sample is gadolinium NBT system. Here gadolinium can go to sodium bismuth titanate, sodium bismuth, barium side. Here one peculiar feature we observe is very important, amphotropic phase. Gadolinium may go to the titanium side. Okay. So what we observed, we fitted the data with A site also, B site also. I am presenting the data of the fitting B site as well as A site. The best fit we observed for the B site. This is the data and these are the fitting. Okay. Statistic reflections that are available at 39 degrees. Here we conclude that gadolinium is actually going to the A site as well as B site. How? Now we plotted the pseudocubic lattice parameter as well as volume. You can see that this lattice parameter is constant, then suddenly decreases. Okay, so this is a very critical phase. Okay, so after this point 0.02 gadolinium basically goes to the B site, means titanium site, or you can call it AbO3 B site. Okay. So another system also we have called sodium doped bismuth barium titanate. Okay, here sodium can go to sodium bismuth barium, and I will show you what are the results obtained. So this is basically your XRD pattern. This is the fittings we observed, and now I am going to show you what are the lattice parameter. So you see AC in R3 phase, AC in P4MM, R3 in P4 volume. So here also we see that the cerium basically goes to, means minimum is observed up to 0.03, and that is the critical condition. We saw maximum changes in the dielectric property. We obtain maximum strain there. Suppose your dielectric property is increasing, right? So or suppose it is decreasing, right? Suppose you dope with cerium and you have a lattice parameter decrease, so that will basically interpret as chemical pressure or lattice strain. So these are the data, these are the plots that are going to tell you how your XRD data is related to the this dielectric data or electrical data or relaxation time, all this thing. So I would like to conclude here my structural part is that we have basically seen, I discussed about this microstructural part. So here, structural part, here we see the NBT based system, bismuth ferrite based system, solid solutions, various morphotopic phase boundary, all these things analysis can be done here, and this can be correlated to your other relaxation data like dielectric or ferroelectric or all this kind of stuff. Suppose your polarization is decreasing. I am having a sample of bismuth ferrite. Suppose a bismuth site I am doping with dysprosium, right? So dysprosium will switch off the lone pair activity of bismuth. So that will decrease your polarization. So this is all about your structural structural properties, how you do the Rydberg refinement. and how you basically interpret your data. Next is your microstructural properties. Okay, microstructural property means your crystallite size, strain, all these things parameter. Next is one of the most important technique is X-ray line profile analysis, right? So in X-ray line profile analysis, what we do for theoretical point of view, if you see, you will have a XRD data. Okay, but that XRD data will broaden based on different parameters like crystallite size, instrumental strain, like lattice strain, all this kind of parameter will affect, and this will broaden the peak. An important thing to note is that broadening basically happens at the lower part. Okay, FWHM can give you the broadening, but it is the average property. But if you want to look for the real broadening, you have to look for the lower end of the peak. This is the peak which you are going to see. Okay, the lower end is basically show you how the peak is actually broadened. So it is very important. So broadening happens due to crystallite size, microstrain, and disorder. Okay, so how we are going to calculate all this, right? So first of all, method is variance range method. In variance range method, we basically what we do, we basically calculate the variance of the peak, and we basically calculate for that variance, we basically calculate the range. Okay, so by plotting this, if you calculate this, this is alpha is range, W is variance, cos theta is the angle, lambda is the your wavelength, S is the strain part. Okay, so if you plot a graph between variance and range is 2 theta, you will obtain a straight line because this is a linear equation. Okay, and from this slope you can basically calculate the lattice size. I'll show you one graph I have. Yes, so this is a BO4 based system. We calculated this method using variance range. So crystallite size came up to 20 nanometer because it is a combustion synthesized sample, and this sample this data has been reported in material chemistry and physics. So we took one peak and we analyzed the variance and range by employing these equations. So you can also do that. This is a very good way. Next is Fourier method. Okay, so in Fourier method, what happens? The total broadening will be like size, strain, and this lattice part. Okay, so if you do that, this analysis Fourier deconvolutions all the part, you are going to get the distribution. How you that go distribution looks like? This is like suppose I have the TEM result here. This is Fourier result. You will have a distribution of the crystallite size. Okay, and it will say that for VO for GDM system, I am showing this published in I think Material Research Express. So for all the samples, you can see the distribution. Okay, so average crystallite size is nanometer, and the same data you can correlate with the TM data. Basically, this is X-ray line profile analysis, so it will give very closer to the observed data. Okay. Next, one other sample we obtained for the yttrium manganite. You can see that there is a distribution, and for this bismuth ferrite we got 20 nanometer, and for higher composition due to more strain we got lower particles around 10 nanometer, and this is a crystallite size strain plot. Okay, so these are the plots you can obtain using Fourier analysis. Okay, so this is like a Fourier size coefficient you have to calculate, you have to deconvolute, so you can use this method. One of the major software that is available is called BREAD. Another software is available, WPPM, whole pattern powder diffraction fit. Another is XFit. There are different softwares are available in ICCDD, and these are all free, and you can employ them to calculate this. Next, another thing is your Williamson-Hall plot. Okay, so Williamson-Hall plot is basically your beta is FWHM, cos theta is basically your diffraction Bragg angle. This is your strain. This is K is constant, it is around 0.9. This is lambda wavelength. This is particle size. What we do, we basically calculate the lattice. We basically calculate the FWHM of peak. So beta is FWHM. By fitting with any software like Origin, you can calculate, and from the intercept you can calculate the crystallite size, and the strain you can calculate from here. Okay, and if you see the data of some of the plots, I can show you that this is beta cos theta and this is sin theta. This is the data for dysprosium doped barium titanate. So you will get linear plots. So these are the different reflections you have. This one we call Williamson, and here particle size basically ranges from, this is barium titanate solid state synthesized sample, and I remember I remember this is basically around more than 100 nanometer. Okay, so all the time nano sample we basically understood by 100 nanometer below. Okay, so next is I like to come back to own. Yeah. Mm. Yes. Okay, so what we discussed today previously is that in Rietveld refinement, I'm coming just back. Rietveld refinement, you need one instrumental resolution file, which is basically your instrument will give, and you can create that by doing a lab 6. It is a compound, lanthanum hexaborate or in a silicon standard sample. Put that in your standard XRD pattern, standard XRD, and you can collect the data, and you can put the lattice this broadening parameters there. You can find this in foolproof example files. I hope I have it. I think my PC. I think response. Yes. So these are the different type of IR files available. So you can select any IR file. You can see that what are the samples for your data. You can insert it and you can import the instrumental resolutions file. So what I like to tell more is that I hope this XRD diffraction analysis like Rietveld refinement, right? So you can, I hope you have some idea about that. Next, yeah. So I'd like to conclude now that what we have done today, we have understood the Rietveld refinement using foolproof package. We have different kinds of samples like bismuth ferrite, a magnet-related compound, then gadolinium manganite, dysprosium manganate solute solution with bismuth ferrite, and this ferroelectric system like NBT-BT system. We have done the Rietveld refinement. We see how we basically analyze the data, and next we see the microstructural plot and all this thing. So now I'd like to ask any doubts if you have. You can, this is now. Um, any student has any doubt, I will be more happy to discuss.
Anybody wants to ask questions, sir is here,
and I'd like to tell that if you want to have a collaborations with me, you can always welcome. So if you want to visit Sri Sri University also, you are also welcome. So that is I'd like to request all of you.
you have that facility, XRD facility and all.
Ma'am, most of the samples collect at we don't have XRD, but what we do basically with my collaborations with IITs or NITs, that's what we do.
And one if you are telling that CIF file is necessary for this Rietveld refinement, so if I have raw data file, can we go with that raw data file for this Rietveld refinement? Actually, RD file I have the RD file of some sample.
See, that is the sample data. That is the sample data file, right? Means your own data. Okay. CIF file is a model file which you basically feed. Yeah. So that model file you are basically going to download from the websites I have shown you here. So these are the websites that are available to download the crystallographic information file. Okay. So from here you get a model, and you have your own XRD data. You are going to basically match them. So that thing we are doing. Okay. So what kind of samples you have synthesized, ma'am?
Sir, basically my work is on BZT, barium zirconium titanate, rare earth.
I had some data. I had some barium zirconium data, but I forgot to show. I had some data. I have submitted to recently to this IEEE journal, so it is under review. So, yeah. So if you want any kind of discussion on that, we can do that. So it is the barium zirconate titanate actually influences me because it has a paraelectric structure at room temperature, and it has a very less, loss. It has very good less loss, and structure is around, I think, cubic PM 3M. So it is a very good structure, relaxer structure. So it is a very good sample.
Yes, sir.
So
Actually, I have gone with this morphotrophic. You discussed the MPV boundaries.
yes,
So
yes.
my
Which
particular
sample you have?
composition, sir, ZR 0.05.
0.05. Okay,
Yes, sir.
okay,
So room temperature it has MPVs. So
okay,
we
okay.
have reported this.
Okay.
Hmm.
MPBs are little critical, ma'am. Means to report the MPB structural data has to be
Sir,
very good.
sir, it is reported by Rajiv Ranjan, ISC Bangalore.
Okay.
Actually,
Yeah, yeah, then
they
yeah, yeah,
have
I know,
gone
I
through
know,
neutron diffraction.
I know. Actually, reporting this, I know Dr. Rajiv Ranjan from ISC Bank. His papers are really good, but the morphotopic phase boundary, if you see the sodium bismuth titanate, they sometimes report CC, sometimes they report R3C. It is all about sample synthesis, ma'am. Which sample you are having?
They change.
Yeah. If you pull the sample, the crystal structure will change. Sample
Hmm.
synthesis conditions create a bigger role here.
Hmm. So
So,
participants want to ask?
yes, yes, I would like to
Hello.
receive more questions.
Yes,
Yes,
yes.
yes.
Praveen Kumar, please.
Yes, yes, ma'am. Sir, I want to ask if we are working on any new type of structure, like whose XRD file or whose JCPDS file and other we don't have. So, how can we download the crystallographic information? Because in these sites, many times we didn't get the information of our particular
Okay,
crystal
okay,
structure.
okay. That you
So,
are
how can we
asking
done
that.
that?
Yes, yes, I got your question. You are asking that your crystallographic information file is not available, or you do not know the structure of the synthesized sample, right? So in
Yes,
that case, yeah. So in that case, there is a very good software is available called Expo. I'm talking about both experimental part as well as theoretical part. Okay, there is a good software is available called Expo. I'll show you right now. I think I should show that. You should try that. You see that Expo Institute of Crystallography CNR Bari, right? This is the first page, right? Do you see this page?
yes, sir.
Okay, so this software is available, Expo software. So what we do if we do not know the crystal structure, first we go for the indexing. In indexing, we calculate the D positions reflections of each reflection, and we basically run with see, there are different kind of crystal system, like 7 crystal system, many space groups are available. What we do, we calculate precisely our 2 theta values as well as intensities values. Okay, precisely. So this is very important. You have to collect your XRD data very important way. So you run your data here, and it will give you based on the HKL matching, means D positions matching. There are softwares available to Expo is called Trayer is there, then DeepCall is there, then MacMill is there. These are the 3 softwares available. They will match your 2 theta values and intensity values to a particular crystal structure. They will give you possible crystal structure. Okay, that is the first step. The second step is HRTM. You can see the HRTM part. You can see different kind of lattice plane arrangements, all this cell. That is the experimental part. There are called single crystal XRD graph, XRD single crystal. There nowadays you can. This is very difficult to get, but if you do a synthesis of a single crystal, you can also see the crystal structure. Okay. Next thing is, because you are having a whole this powder pattern, you can run your data with this kind of software, you will get a good match. You will get a possible space group, and like 2 to 3 possible space group you will get, and you try to refine that. It will give you lattice parameter for that possible space group. You will give the lattice parameter. It will give you the atomic positions, everything. It will give this software. I mean, it will fit your 2 theta value and peak value. It will fit. It will give possible space groups, and you have to try all the possible space group during the refinement process. And the best match, you can report that as your your crystal structure. I hope, and another thing is that there is a Patterson mapping is there. I hope this is more beyond. It is like a electron density mapping. Okay, so you can plot electron density, and you can also get information is there. Now I would like to also tell, suppose your data doesn't show the ferroelectric hysteresis loop. That means it is a centrosymmetric structure. So all the non-centrosymmetric structures you can easily eliminate there. So all this kind of possible clues, there are hit and trial methods. Okay, I hope my answer is clear to you.
Yes, sir. Thank you very much.
So I request you to try this Expo software. It will help you a lot if you try this. Yes.
Yes, sir. Thank you, sir.
Sir,
I hope
one more question is there.
Yes.
From Shubhasri Sahu. Can you please explain how can we input the data for double phase refinement?
Okay, I have the data, so I'll just show you. So I think this is the Rietveld refinement we have done. I think I'll do this because it was in the middle. Okay. I think we have completed up to this refinement, right? So to suppose I have to dope with gadolinium manganate, right? So this is bismuth ferrite, so I'll close it, yes. Then I'll go to the page here, right? So if you go to the page, you'll go to add phase here, right? So you click here add, and you type it here GDMN, right? And you go to the contribution of pattern, you select the contribution of phase here because it's the extra phase. So the secondary phase you got, so you just put this one, sorry, I'll use this one. So symmetry, so here I'll use PNMA, so it will automatically bring out all the symmetry options. Okay, so you click it OK, then this is okay, the phase is added here, so this is okay. Go to the refinement, here 2 phases will come up, and don't refine the background because background is refined in first phase, so that is enough. So go to the page and put your lattice parameters here, and here in phase 2 put the atoms here. Okay, so after this you can start the run and fitting the process. Is it clear? I hope.
I think she is there. Shubhasri Sahu.
Yeah, so this is the way you basically import the data to this dual phase refinement.
Any more questions from participants? One small announcement for the participants. We have recorded the lectures in YouTube, and I have already shared the link also. So you can watch these YouTube lectures again and again and ask.
Yeah, that is a very good. Yeah.
And I will also share, sir, if you permit, I will share your email ID to the participants. Some of them are asking for the email.
Yes. If you will have to have a collaborations with me, if you have a good XRD data, we can also discuss regarding that. I would be happy to, because my idea is to see all kind of refinement, or means go for a diversity, right? So yes. I have refined many kind of samples, but like more than 100. But I have more eagerness to see more samples.
So
I think someone,
sir,
okay.
Yes, sir, please.
I think someone else is put question. I think.
Sir, actually, they are asking for the email ID.
I think, yeah, I'll. Okay, ma'am, you can share them, or I'll write it here.
Sir, if you please.
Okay, I'll write it. Okay. So this is my email ID, and my personal email ID is so this is my personal email ID. So if you need any help from me or any suggestions or any discussions, I'll be very much happy to do that. Because I love crystallography, so you can always put me questions there.
So I think today's session is over now. Sir, thank you so much for a
Okay,
wonderful
thank you.
session. And
Thank you.
on behalf of organizing committee, our principal madam, Dr. Tanmay, and all other members, I heartily thank you for sharing your valuable knowledge as well as precious time with
Thank
us.
you.
Thank you so much, sir. And definitely we will love to listen you again.
Okay,
Hope to
thank you.
listen you very soon, sir. Thank you so much. Thanks to all the participants for patiently listening the lectures and clearing your doubts. And tomorrow we will have a talk that will be delivered by Dr. Manoranjan Kar from IIT Patna. The talk will be on electron microscopy. So please join us at 12, before 12, so that we can start it on time. So for today's session is over now. Thank you so much. Thank you all.
Thank you.
Okay, sir.